Day 142, Physics, Electrical Power, Calculating Electrical Power. First, reviewing our basic equation, and that is delta V, or just V, equals IR, sometimes called Ohm's law, where V is voltage, or delta V is voltage, potential difference, I is current, and R is resistance. Now over here on the left, here are some prepositional phrases that are used a lot of times as you read these problems that you need to get used to. When they use these in sentences in the problems, it'll say the resistance of a light bulb, or the resistance of the carbon resistor is 50 ohms. It'll say the current through the resistor is 5 amps, and the voltage across, or impressed across the resistor or the element is 12 volts or whatever. So those are some words that are indicators of those particular concepts. Once again, the units for resistance are ohms, for current is amps, for voltage is volts. All right, now power. And it's also related back to mechanical power when we had that first semester. It'll be the same units, you'll see that in a minute. But for electrical elements, specifically like for a light bulb, the power is indicated by the brightness. The brightness of the light bulb. So you're going to need to keep that in mind. For some reason, this is not writing too well right now. But keep that in mind as we do the lab tomorrow. Brightness of a light bulb is its power. Now, the equation is P equals VI, or P equals delta VI. Power, turns out, I'm not going to prove it to you right now, but power comes out in joules per second. And in first semester, that's the same thing it was for mechanical power, and we call that a watt. A joule per second is a watt. All right, and voltage is still in volts, current is still in amps. Electrical power, you can say, is joules per second or a watt. All right, let's calculate, do a couple sample problems, calculate down here below. All right, so we have a sample problem. Let's do part A first. We're trying to find, well, we have a resistor, a light bulb with a resistance of 240 ohms. So part A, we're going to use P equals VI, delta VI. Once again, a lot of times we leave off the delta. I'll put it in here. P equals delta VI. So we're looking for the power. Simple plug and chug. The delta V, the voltage, is 120 volts. That's given in the problem. The current, oh, we don't know the current. So we're going to figure out, using Ohm's law, V equals IR, off to the right here. If we have 120 volts, 120 volts equals I times the resistance of 240. So the current is 0.5 amps. Having trouble with my pen here. All right, so that's our current. So I'm going to bring that back over here, plug that in. That's 0.5. 0.5. So the power here is 60 watts, 60 joules per second. So you can say 60 joules per second, or you can say 60 watts. Either one is acceptable. That's the power of this light bulb. By the way, if you take Ohm's law, which I just had here, this right here, Ohm's law, if you take the IR and plug it in, let me show you that with a different color. If I take this, and you might want to just watch this for a second, and you plug it in for the V over here, you get an equation that can be very useful, another power equation. Bottom line is, if I rewrite, I'll do it in blue. If you make that substitution in the power equation, you get this equation. You get P equals I times R times I. I'll write it down first, but then so you get, you plugged in for V, you get IR times I. Well, to simplify that, that's P equals I squared R. That's going to be useful to us. That's another form of the equation, just combining two equations, Ohm's law with the power equation. You get power is I squared R. where I is the current. So you might want to jot that down, and we'll be using that a lot in the lab tomorrow. Or you can just do it like we did part A, a double-step problem. But using that blue equation, we could have done that problem. Well, it still would have taken us 2 steps. But you'll see sometimes that equation there will save you some time. Not right now, but eventually it will. All right, so part B. It says, what if the power, if R is 200 ohms? Well, if R is 200 ohms, redoing the problem, doing V equals IR again, if you had 120 equals I times 200 gives you a current of, what, 0.6 amps? Yeah. 0.6 amps instead of 0.5 amps. So that's a little bit more current now. So the power, and I'm going to use I squared R here, 0.6 squared times the resistance, which is 200 ohms. And interestingly enough, when you change or have a light bulb with lower resistance, the power ends up to be higher. Let me see what it is. So you get 72 watts. Even though there's less resistance, well, the main thing is when there's less resistance, that's 72 joules per second or 72 watts, the current goes up. And when the current goes up, if you look at that blue equation there, the current is squared. So the current has a big factor in power. As the current goes up and you square it, it increases your power more so than the amount of restriction that the resistor supplies. All right, so that's 72 watts. Part C, the energy used in one day for the 240 ohm bulb. So going back to part A, and I'll do it underneath part A, so part C. Well, that kind of goes back to first semester, and that is, this is an equation from first semester. Power equals energy over time. Power equals energy over time. That says energy over time. That's the definition of power from first semester. Or in other words, the energy, which is what we're looking for here, is the power times the time. It's the amount of joules per second times the number of seconds, loosely speaking. So energy, I'm just going to use E for energy, equals the power, P, times the time, T. So the energy used for this bulb, the 60-watt bulb, 60 joules per second, is 60, the power, times the time, which is 1 day. Well, 1 day, you have to do the conversion there. How many seconds in a day? You can't put in just 1 day. So you have to, I'm going to go do that off to the side. Well, 24 hours. I'll do it over here on the right in blue. I got 24 hours times 60 minutes in an hour times 60 seconds in a minute. That gives me a total of 86,400 seconds in 1 day. 86,400 seconds in 1 day. So I have to put that into the equation over here. I'll do it in blue again. 86,400. That's a comma there. Okay. So if I have 60 joules per second times 86,400 seconds, I get a total energy, change into red again. I'm going to do it right over. So the energy here, sorry about this. Hopefully you got space there. 60 times 86,000 is 5,200,000, 5.2 megajoules, or 5.2 times 10 to the 6th. 5,200,000, rounded off to 2 sig figs. 5,200,000 joules. That's 5.2 megajoules. I'll circle that in blue. That's my answer for the amount of energy used by that bulb converted to light and heat in one day.